So, now we are getting onto the content. So, let's start with what the modeling motion section of the syllabus actually requires you to do. So, the syllabus requires that you are able to examine momentum, force, resultant force, action, and reaction, consider constant and non-constant force, understand motion of a body under concurrent forces, consider and solve problems involving motion in a straight line with both constant and non-constant acceleration, including simple harmonic motion, and use all of those expressions below for acceleration. Those are all on your formula sheet as well. We'll get to those. This is what you need to be able to do for the modeling motion section. Just another quick tip as well is to make sure that you understand the difference between the cognitive verbs, and that's available on the QCEE specialist syllabus under definitions. So the cognitive verbs are underlined here. So examine, consider, understand, consider, and solve. This isn't as relevant for the math subject, specialist in methods, but it still is useful. It is more so useful for your sciences, where there is a difference between like defining and then explaining and solving. But most of the cognitive verbs in specialist are going to be centered around solving. All right. So, what we're firstly going to focus on is momentum, force, resultant force, action and reaction, and constant and non-constant forces. So, momentum is given by mass times velocity, right? And force is the rate of change of momentum in a system with respect to time, or in other words, dp dt. So we have a relationship already between momentum and force. We also know that force is equal to mass times acceleration, which is also known as one of Newton's laws, where the units for force are newtons, or in other words, kilogram meters per second squared. So, force, acceleration, velocity, and displacement are vector quantities, which means they have direction as well as magnitude. So make sure you always give direction in your answer. This is really important. It's really easy to forget direction, especially if it's not something where you need to find an angle. If it's just kind of like upwards or downwards, make sure you still write that. And then make sure, of course, if you're finding a vector quantity, that if you need to find an angle direction or a bearing or something along those lines, make sure you find that too, because otherwise you'll lose a decent chunk of marks out of the question for that. All right. So this kind of stuff we've just gone through is pretty basic stuff. But I'd say the most important to remember off this slide is F equals ma. Of course, I guess most people know of it, but what I'd recommend doing is in your notes, make sure you kind of highlight it or put it in a different color, because a lot of the time when you're doing one of these modeling motion questions, if you come to a point where you don't really know where to go, one of the options you can usually apply is F equals ma. It's kind of one of those equations that you maybe forget about, but realize that even though it's not on your formula sheet, you can actually apply it. Alright, so these definitions that I've given aren't wrong, but they're not really that practical by themselves, because in reality, there are lots of different forces acting on a particle, not just kind of one force in one direction. A lot of the times we have particular forces all pulling in different directions. We might have an applied force and wind or friction, a lot of things going on at once. So, what we usually deal with in specialist is the net force, and the net force is the sum of all of the forces acting on an object, right? As a result, our resultant force is given by F net equals the sum of F, right? The sum of all of our forces. Again, you don't really need to remember this equation, it's just a concept you need to remember. So, as a result, to find the acceleration of an object as a result of a few different forces acting in different directions, we need to know the net force and the direction of that force, because we know that F net equals ma. So to find the acceleration, we need to have the mass of the object, and then we also need to have the net force, right? So a lot of these questions that we're doing when we're getting into modeling motion look at finding the net force. So usually what we're going to be doing is looking at a few different vectors, adding the components of those vectors together, and finding a resulting force. So typically what we need to focus on is mostly just kind of vector resolution. When we get into more difficult like rates of change and stuff like that, it's more focused on the actual equations in your formula sheet. But when we're getting into this kind of modeling motion and understanding net force and momentum and all that kind of stuff, it's really just about vector resolution. So let's have a look at actions and reactions. So the action is the force of one particle on another, such as pushing a door open. And a reaction is a consequence of Newton's third law. So this is where the second particle exerts an equal and opposite force on the first, i.e. the door exerts an equal and opposite force on your hand. And this is what you feel pushing back against you. So, some common reaction forces you might encounter is tension, which is a force through any string, chain, rope, or kind of any like similar like string-like object. And normal force. So normal force is the force opposing gravity that an object exerts on another. One thing I just want to make note of with regards to tension, if you're ever asked about tension in a question, the force of tension is just equal to the force applied through that object, right? So if a question tells you that there are, 10 newtons of tension applied through a string, that just means that the applied force is 10 newtons. There's nothing special about it just because it's tension, right? The only time you really need to consider the fact that it's a string, chain, rope, or whatever is where you kind of have like pulleys and you have like maybe multiple masses on pulleys. But again, you're not really focusing too much on the fact that it's a string, chain, or rope. You're mostly just focusing on the effect of the masses on one another. Anyway, just a quick little note in case you're getting confused about that. And again, with normal force, remember the normal force always acts perpendicular to a surface. Where you might see this in specialist is if you're doing an inclined plane question, and you do come across those in externals and mocks. If you have an inclined plane, The normal force is perpendicular to the plane. It's not perpendicular to the ground, right? So what this might look like is an inclined plane like this. The normal force will look like this, right? It's not going to be perpendicular to the ground, it's perpendicular to the plane. All right. Just because the forces acting on both objects are the same doesn't mean the result on each object is the same, and this is Newton's third law. So, this is the very classic example, I'm not sure if you've heard of it, of a person and a spaceship. I think it was one of the first um, uh, expeditions out in space, and they took an astronaut out to space, and they tethered him to the spaceship, and he went off and explored around in space in his spacesuit. Then when he went to try and get back into the spaceship, he couldn't, because every single time he touched the spaceship, he just kind of bounced off, like quite violently, right? And everybody was really shocked and confused. They were like, why is this happening? Right? Until eventually they realized, this massive team of physicists and experts taking people up to space realized that they forgot about Newton's laws, which is that there will always be an equal and opposite reaction to every action. So, when the astronaut was touching the spaceship to try and get back in, he was exerting an action, right, which was moving the spaceship a tiny, tiny, tiny bit, because it's very big. So he's putting in action, and it's moving the spaceship a tiny bit, but the spaceship is making him bounce back because he's so much smaller. So it's exerting an equal and opposite reaction on him, but he's experiencing it far more because he's so much smaller, that it requires a lot less force for him to move. And this is exactly the concept that we're seeing here in this question. So, we have a sumo wrestler with a mass of 200 kilograms running into a gymnast with a mass of 40 kilograms. As they collide, the sumo exerts a force of 800 newtons on the gymnast. Find the force exerted by the gymnast on the sumo and the resulting acceleration experienced by both people. Right. Pause the recording, have a go at this question if you're feeling confident. If you're unsure, don't worry about it. We're just going to go through the solution now. So, let's quickly draw a diagram of what we're seeing. So we have our sumo wrestler, right, running into a gymnast, right? So the sumo exerts a force of 800 newtons on the gymnast. Find the force exerted by the gymnast on the sumo, right? So remember, every action has an equal and opposite reaction, meaning that the force exerted by the gymnast is going to be the same. It's going to be 800 newtons. Now we need to find the resulting acceleration experienced by both people. And this is going to be different because both of these people have significantly different weights, which means it requires significantly different amounts of energy to move them. So, what we know is that F equals ma. So the force exerted is 800. the mass of the sumo wrestler is 200 a sumo. This gives us an acceleration of 4 meters per second, and this is just going to be away from the gymnast. Applying this again for our gymnast, we're going to have 800. Her mass is 40 a gymnast, and this gives us an acceleration of 80 divided by 4, which gives us 20 meters per second away from sumo wrestler. We don't actually have the directions, I don't believe. No, just that they're running into one another, so we can't provide whether it's left or right or up or down or whatever. And the force exerted by the gymnast on the sumo will just be, I guess, like towards the sumo. So, as you can see, the acceleration experienced by the sumo wrestler is a lot less than the acceleration experienced by the gymnast, and that's because the gymnast is so much smaller. Alright, now what we're looking at is a more difficult example. So in the previous example, our two forces were acting in the same plane. They were acting directly against each other. In this example, however, they're not acting in the same plane. So, as a quick tip, when there are multiple forces acting on an object, it always helps to draw a diagram of what's going on. Here we have two people pulling on a rock. Both people exert a force of 1,000 newtons, but person A pulls to the right and person B pulls upwards. What is the net force on the rock, assuming a smooth surface? Normally, when we're given two forces acting in different directions, instead of just head to head or tail to tail like we were just before, with the sumo wrestler and the gymnast, what we need to do is resolve forces into horizontal and vertical planes. Or what you can also do is you can draw your forces as vectors if you have the angles, and you can use like trig and angle rules like the Z rule and co-interior angle rules and so forth to actually do some vector resolution, just depending on what works for you. Alright, so for this example here, what we're going to first do is draw a diagram. So, both people exert a force of 1,000 newtons. The person A pulls to the right and person B pulls upwards. So, person A, person B. Both these arrows, 1,000 newtons. And we want to find the resulting force, F net. Have we missed anything? No. So, here we have I and J. Alright. As you can see here, our vectors are added head to tail, which is what we need to do to find our net force. So, as you can see here, we have a right-angled triangle because our horizontal line is directly horizontal and our vertical line is directly vertical. So it's a right-angled triangle, meaning we can just actually use Pythagoras to find our net force. Squared, and we're going to have 2 times 1,000 squared. And this is going to give us 1414.2 newtons. And now we need to find the direction at which this force acts. Because remember, force is a vector quantity, we need the direction and the magnitude. You could use a trig to come up with this angle here, but for me personally, because this is an isosceles triangle, we already know that this is going to be 45 degrees to the horizontal, because it's an isosceles triangle. But you can just feel free to use just use trig there if you'd like. Another way you could have recognized that is remembering our special triangle, the isosceles one, how this angle is 45 degrees. So you could have done it that way as well. Alrighty, so that was our question there. Pretty straightforward. Now we're going to move